So, okay, so last time the last thing we did before the midterm was to say that maximum work that can be done by a system is during reversible change. Okay, remember how we proved this? What we did was to set up an expansion process in pressure volume space where we said either the gas expands reversibly going like this, or you just bring it down to the final pressure and then it kind of goes to the other side, right? And then we said that the work that is done by the system is going to be integral minus P external dV in both cases, right? In this case, we were able to use the equation of state because it's reversible. And in this case, no equation of state because it is not reversible. And in both cases, the work done by the system amounted to the area under the curve, right? And as you can see, the red one has higher area under the curve while the blue one has lesser area. So this showed that you can get more work out of a system if the change is reversible. Now this we proved for a specific case, right? We assumed it is an ideal gas, and it's an isothermal expansion, right? We assume these two things. But the main message here was that minus delta W reversible is more than equal to minus delta W irreversible. Why did I put minus sign over here? Because when you're talking about the work done by a system, it's going to be negative, right? So if the system did minus 10 kilojoule work on the left side in the reversible process, then in the irreversible process, it probably did minus 5 kilojoule work, right? So you were able to get less work out of the system. So we showed this for a very, very specific case. I was earlier planning to go through the nitty-gritties of how to prove this for the most generic case. I'm not going to do that. The basic idea is same. It's a bit of bookkeeping, but Callan proves this for the general case. You should read it, and I'm going to ask you to do it in the next homework, okay? So please go through it and you will summarize your ideas, or you will work through the proof yourself in the next homework. So go through it. It's a bit of bookkeeping, but it's important. There is nothing profound. The main message remains the same. If you have any system, for example, you are interested in converting fuel, glucose into energy, getting work out of the food that you have eaten. And if the change is happening reversibly, you will be able to get more work out of the glucose as opposed to just irreversibly. So this simple mathematical inequality is quite important, and this is going to play a role in what we are going to do next. Any questions about this? So what we are going to do next is really going to be it's known as Clausius inequality. Okay, C-L-A-U-S-I-U-S. C-L-A-U-S-I-U-S. If you forget the name that it's Clausius inequality, that's okay, but you should not forget the relation that we are about to prove next. This inequality is really the basis of the next many, many classes, okay? So it's very important to understand what's going to happen here, yes. So we saw earlier, a few classes before, that ds is equal to delta Q reversible by temperature. Anyone remembers how we proved this? What do you think? No, simple. What do you think? You remember? Yeah. Let's try. Let's write down the first law of thermodynamics. Okay, work with me. What's the first law of thermodynamics? dE is equal to delta Q minus P external dV, right? Let's just say it's pressure expansion work. So then we said that this is true for any process, right? When you're going from, so yes, in a sense, you're correct that it's by looking at paths, but so you're correct in that sense. So we said for any reversible, any generic path, dE is equal to going to be delta Q minus P external dV, right? And then we said if it is a reversible path, then dE. How did we prove this? No one remembers? I'm giving it too much hand.
You use the integrated first and second.
We integrated the first and second law, right? Then we said that also we know that dE is equal to TdS minus P external dV DE is equal to TdS minus PdV, and we ignore the chemical potential part, for a reversible path, right? If this system follows the equation of state, if change happens irreversibly. So now whether you go from A to B irreversibly, or whether you go from A to B reversibly, the dE should not change, right? The dE we should be able to compare. E is a state function, right? It does not depend on how the process was carried out. Therefore, delta Q should be is equal to TdS if the process is being carried out reversibly, right? This was the idea. Okay. So you should not be blanking when I ask you things like this, and not just you, but anyone, because this is fundamental. If you forget this, you're going to get totally lost in the remaining of the semester. Okay, I can promise you, you will get lost. This is so fundamental, you should not get lost in it. So ds is equal to delta Q reversible by temperature is really, really basic. And we did this. Now the question is, what about irreversible change, right? Can we construct a relation between ds and delta Q for irreversible change? By irreversible, I mean if you make it very, very small, then it becomes reversible. You can call it irreversible or actual. How should we go about this? So let's think first, if it is irreversible adiabatic change, then what can we say about ds for such a process?
DS is not zero.
A little bit more than, it's more than zero, not just not zero, right? That is exactly the postulate, right? Callan's postulate. It said that for an adiabatic change, the entropy goes up. If it was negative, that means if it is zero, then it means it's a reversible change. But if it's irreversible, then the entropy goes up, right? So this gives us some hint. But adiabatic, what is the meaning of adiabatic in terms of delta Q? Zero. So this gives you a sense of the expression you might expect to be true in general, right? Can you guess what should be the connection between ds and delta Q? Greater than equal to, right? So we expect, we haven't proved it yet, but hopefully you have some intuition that ds should be more than equal to delta Q irreversible by T. And if it's irreversible, then it should be strictly more than, right? Our ds should be more than equal to delta Q by T if you don't know whether the process is reversible or irreversible, right? So this is known as, either of these is known as Clausius inequality. And let's prove that it is true. It's quite easy. The way to prove this is going to be using this relation, equation number 1 that we did last time, that you get more work out of a system if change is happening reversibly. If you are doing irreversible work, it means the work that you get out of a system is going to be smaller. So in order to prove this, we will again look at two states of a system. So let's call it proof is really quite simple. Going from A to B, and we will consider two pathways, okay? Pathway number one is an irreversible pathway. Let's call it I. And this other pathway is a reversible pathway. It can go in both directions. Let's call it R. Okay. So dE is equal to delta Q plus delta W. This is true for both I and R, right? That's just, yeah, Sophia, you have a question?
What's the difference between the DQ irreversible and then the other DQ? Is that just general?
Reversible or irreversible. Notice the equality showed up, right? So if it was reversible, then ds would be equal to delta Q by T. So in this process, in this way of going from A to B, dE is equal to delta Q plus delta W for both I and R, right? That's just first law of thermodynamics. However, only for R, for the reversible path, we know that dE is also equal to TdS plus delta W, right? Because we just recapped that delta Q is equal to TdS for reversible path, right? And you're going from A to B. E is a state function, so dE should be the same, right? The value, the change of the value of dE should not depend on whether you went through I or whether you went through R. So this together should be equal to this together, right? Let's call it equation 3. Let's call it equation 4. dE should be same for I or R, okay? So delta Q plus delta W, and let's call it actual now to distinguish it. By actual, and it's nothing profound, by actual I mean something which is reversible or irreversible, right? An actual process can be one of the either. It could be either reversible or it could be irreversible. So delta Q actual plus delta W actual, which is this part over here, should be equal to TdS plus delta W reversible, right? Correct? Everyone happy with this? You say you're happy, but you all look very unhappy. I mean, it's a thermo class, so it's fine. So
What's the actual,
reversible or irreversible, any of them. It's not profound, it's really simple.
no, I mean, why are you using that subscript actually?
Because then I have to worry about equal or unequal and things like that, because I want to keep using the inequality, right? So TdS, so if we transform this, it will become ds is equal to delta Q actual by T plus 1 by T delta W actual minus delta W reversible. You could very well write delta W irreversible. If you didn't like actual, just work with irreversible. It's the same thing. It won't make much of a difference. The idea is the same. Now we can use in equation 5. Yeah, let's just do irreversible. It's going to confuse. If you have already written actual, you don't need to scratch it. It's fine. It's really irrelevant. So delta Q irreversible, delta W irreversible. Okay. Now we know something about this thing in the square bracket. We just saw this in equation number 1, that minus delta W reversible is more than equal to minus delta W irreversible, right? So we can use that over here. And what does that tell us? That tells us, so let me write down equation 5 once again. Equation 5 was ds is equal to delta Q irreversible by temperature plus 1 by temperature delta Q, not delta Q, delta W irreversible minus delta W reversible, okay? And equation 1 showed that, what did equation 1 say? That minus delta W reversible is more than equal to minus delta W irreversible, or delta W irreversible minus delta W reversible is more than equal to 0, right? What did we just show? We said that this thing is therefore more than equal to 0, right? So what does that mean? That means that ds is equal to delta Q irreversible by temperature plus something positive. And why can we say that? Because we know temperature itself is positive, right? The denominator here, 1 over T, that is positive. Therefore, ds is more than delta Q irreversible by T. Okay? So this is really simple, but really, really important. Why is this so important? The reason why this is so important is, let's say you have a chemical reaction happening, A plus B going to C plus D, okay? Or some process, doesn't even have to be a chemical reaction. And let's say this chemical reaction was happening in a thermally insulated container. Okay, if it was a thermally insulated container, what can we say about delta Q? 0. Does it matter whether it's reversible or irreversible? No, right? So what's our Clausius inequality now? For the change to be irreversible, ds should be positive, right? So now, if SC, the entropy plus of C plus entropy of D minus entropy of A minus entropy of B is positive, the reaction will proceed in the forward direction. Okay. If this is negative, the reaction will proceed in the backward direction. If this is 0, the reaction will be reversible. You will not have anything. So this is why it is so powerful. And what we are going to do in the next few classes is to make this reaction was happening in a insulated container, right? That's kind of boring reaction. You can't see anything because it's insulated. So how do we make it practical? That is the whole point. So in other words,
Entropy a measure of spontaneity.
yeah, exactly. That's what I was going to say next. Are you in my brain? that's exactly what we're doing. So in other words, and I'm going to start this because this is so important. ds is equal to delta Q reversible by temperature. Huh? No, you're okay? Unhappy? Oh, okay. He was punching you or something. Oh. Don't get violent, guys. If ds is equal to delta Q reversible by temperature, this means both the forward and backward processes are possible. So when you read this, often it becomes confusing. It's like, what does it mean both forward and backward are possible? It means that if you change the driving conditions just as slightly, one of them will keep happening. But if you change the driving conditions back in the other direction, the other one will keep happening. Remember, when we talk about irreversible change in the very beginning, that's what we said, right? We have a piston. If you just yank it like this and you make a small change, that's not going to change anything. But if you're moving it slowly, then, and if you reverse the direction, then the change will keep happening in the other direction, right? So if ds is equal to delta Q reversible by T, then forward and backward processes both are possible. If ds is more than delta Q by T, then forward process is possible. And the word we use for this is known as spontaneous. You won't have to do anything. It will on its own like to go in the forward direction, right? If ds is less than delta Q by T, then backward process is spontaneous. So this is the first time we are looking at the word spontaneous. Before thermodynamics, if I asked you what does spontaneous mean, just from English, what would you have said? What do you think? Yeah. Does it give you a sense of time though? It does, right? But that's where thermodynamics kind of misuses it. There is no notion of time here, which is kind of ironic. Just because you can see that A plus B to C plus D is spontaneous, it still very well might take age of the universe. Okay, that's the boring part of thermodynamics. It's not telling you, it misuses the word spontaneous. Spontaneous does not mean immediate. Spontaneous means, you know, it will happen. You just have to wait. Yeah? So it's kind of misleading. Just like thermodynamics, the name itself is misleading. There is no dynamics, right?
So do we use the Gibbs energy because it's experimental?
You're jumping too far.
No, I'm
Yes,
saying
yes.
because that's the
We don't know Gibbs free energy yet. The reason why we will think about these free energies and all that is because
it's just experimentally easier to measure.
exactly. So this is complicated, right? First of all, yeah, we will get to that. We will make this all useful, but give all these free energies and everything. I mean, you have probably seen it at some point, but if you have forgotten, don't worry. We will come to free energies very, very naturally. Okay, but you're absolutely correct that so. As Callan also says around this point, that all of remaining thermodynamics is to just make these things useful, right? Practical. But otherwise, the key idea that you have was already captured in the second postulate, that the entropy should increase if it's adiabatic reversible change. That had captured everything.
I had a question about that. So for a process, is the entropy function that you have unique?
Entropy is a state function.
Yeah, but does the exact functional form of entropy, is that unique? Because I asked the midterm question, there are two, like there's one way that involves a lot of ugly integration, or the other way Callan does it is quite, I'd say, nifty or unique. But in both cases, even in the one we did in class versus what you have an integration constant that's undetermined.
Yeah, yeah.
So you can't have complete thermodynamic information.
Yeah,
It's
sure.
not a fundamental.
Sure, sure.
Since you're getting that like experimentally,
yeah,
are you going to be? Can you say that using two different theoretical methods to derive it?
Depends on how much information you have. If you have all three equations of state, then it will be unique.
Okay.
If you have two equations of state, then no.
But the only thing that varies there is that constant of integration, which is not, doesn't depend on n, b, or e.
Well, sure. In that case, we saw there is a constant of integration, but you could imagine maybe it is something more complicated than that, right? So I won't bet my life on it. But one thing I can say for sure, if you have three equations of state, then it will be unique. Right. If it is two equations of state, maybe it is unique up to a constant. Maybe it is even worse than that. I need to think more. It's a good point. Will it always be unique up to a constant? Because if that is true, then that's already quite useful. But I think it's not true for many, because you found it to be unique up to a constant because you were using a specific equation of state. You were using ideal gas law, you were using binary gas law. I could cook up some equation of state where there is actually, it's different even more than just a constant. Right?
But for any general process, you won't be able to.
There is no way to guarantee. So if you know two equation of state, maybe the examples we saw in class and in midterm, they differ just by a constant. But in reality, they could differ more than that, right? Okay, so good point.
So in experiments, we measure the change in entropy, not just the entropy. So that constant will be like cancelled out or something.
But yeah, that helps us. We can get away with that. That's why it's not too bad. But if the difference is more than a constant, then no, right? So that's why we have to be careful. So, okay, one moment. Yeah, any more questions? Keep asking questions. It's good. Otherwise, I will go too fast. You know? It's a problem in thermodynamics. You can easily cover too much, and then there is no point. So, what was that? My notes sometimes have a fractal nature. You know, like go to page 18, then come back to page 5, then go to page 4. I lost. Where was I? Okay, good. So one thing this is already making it quite clear that the way to find out whether something is going to happen or not, the answer lies in two things: entropy and heat, right? It's really by comparing their difference. Entropy is a state function, On the right, you have a path function. But it is really by looking at these two things that you can see whether something is going to happen. And this might sound to you like just abstract stuff, but it's actually super profound. For example, who here is interested in looking at nanomaterials? Many of you. Can you have phase transitions in a 1D nanomaterial? Turns out no. Graphene is 2D, right? Even carbon nanotube is actually 2D if you think about surface. So you can't really have a 1D material which has a unique ordered phase that can exist. And the answer lies in something like this. You will see that in StatMech in next semester as to why that cannot happen. So this set of relations is like super important. It does everything. If you remember this, you can do everything. You will get to free energies and all that business because it makes it practical. But this is what is useful. So it already shows that maybe we should take some time to think about how to measure heat, right? If we don't know how to measure heat, how will we be able to do this, right? And heat is a path function. And it turns out it's actually the easiest thing to measure. There are lots and lots of instruments, calorimeters and things like that. I mean, I'm a theorist, but even I have done those experiments in undergrad. We use a calorimeter to measure, the heat given to a system. So let's talk about heat and how do we measure it. So, and why do we care so much about heat? Because firstly, it matters through the Clausius inequality, and secondly, it can be measured through things like calorimeters. It's actually way easier to measure than anything like entropy. So we know that dE is equal to delta Q plus delta W, right? This is true for absolutely everything. This is just conservation of energy. Or dE is equal to delta Q minus P external dV plus delta W additional, whatever additional work you're doing on this system. In what's going to follow next, we are going to focus on only pressure volume work, okay? No additional work. And you can generalize it later, but this is already quite useful. So if you're doing that, then dE is equal to delta Q minus P external dV, okay? Now let's think about two types of special processes. So in general, this is not telling us what to do with delta Q. Turns out for two special types of processes, delta Q becomes very easy to deal with, okay? Additional. So case one, we are going to look at constant volume process. And let's number the equation for today, 3, 4, 5, we do 6, I introduce 6. So let's call it equation number 6. Constant volume process means dV is equal to 0, right? There is no change in volume. Therefore, dE is equal to delta Q. That's very interesting, right? Because on the left side, you have change of a state function. And on the right side, you have change of a path function, right? It's telling you that if you do the process at a constant volume, the heat given to a system will actually not depend on how you do the constant volume process. It is a state function. You can always calculate it just by studying the change in energy at the end states. Does not matter what path you take. So this is very interesting, at least to me, because this is true for reversible or irreversible. Simply does not matter because the left side is a state function, right? So in other words, delta Q, constant volume, reversible or irreversible is equal to dE. Okay. So that's a constant volume process. Now let's think about a constant pressure process. So for constant volume process, we got a nice answer that delta Q is equal to change of a state function. So the question we would like to ask is, there exists some magical state function for which d of that state function, so this was for constant volume, and we are asking if there exists such a state function for which this is going to be equal to true. Unless you have taken thermodynamics or physical chemistry before, it should not be obvious to you. Why should it exist, right? So many of you are dying to say it's enthalpy, as you have studied it. Yes, so there exists such a state function. It has the symbol H. It's known as enthalpy. If you go and do a survey of people who have done thermodynamics in high school or even chemistry majors who 10 years later are doing some other jobs and ask them, do you remember what's energy? They will say yes. Do you remember what's potential energy? They will say yes. Do you remember what's entropy? They will say yes. They might even say yes to free energy. Enthalpy is one thing they forget. I've actually done it. I've seen it. People forget enthalpy because it's kind of shows up in the middle of nowhere. When we do Legendre transforms later, you will see why it's actually quite fundamental. So this enthalpy is defined as E plus PV. And we are just going to prove that for a constant pressure process, delta Q, whether it is reversible or irreversible, is again a state function. We don't have the liberty to say this for delta Q for other processes, okay? These are very two special processes where delta Q happens to be a state function. That's kind of makes it powerful, right? That's why. And also it's natural to think about constant volume and constant pressure processes because these two are typical scenarios in chemistry, right? Your chemical reaction is either happening in a beaker, which is exposed to the atmosphere, then it's a constant pressure process, or it's happening in a test tube, which you have closed on the side, then it's a constant volume process, right? So these two are quite typical. If it's a constant chemical potential process, then I don't know. You can go and think whether there is an answer to this. Maybe I'll give you a problem on that. So let's try to prove this. Proof is quite simple. We have dE is equal to delta Q minus P external dV. Okay, it's a constant pressure process. So there is no point in dangling P external or P or things like that. There is one pressure, it's constant pressure, nothing is changing. This is kind of subtle. So typically someone will come back on Slack and ask me, wait, why did you do that? Because it's subtle. If you think about it, you can get confused. Because constant pressure process. Okay, where do we go from here? Let's write, I will write this last equation on the next page. So we wrote dE is equal to delta Q minus PdV. It's a constant pressure process. So we can do something is to magically add plus VdP. Why? Because it's constant pressure, right? We are just adding 0 to it. There is nothing has changed. We don't just have to add VdP, we could also subtract VdP. It's 0, right? Who cares, right? We just subtracted it because this is 0. What does that mean? That means that dE is equal to delta Q minus d of P dV, d of PV, right? Or dE plus dPV is equal to delta Q for constant P process, or d of E plus PV is equal to delta Q for constant P. And this is what we defined as enthalpy, right? Therefore, dH is equal to delta Q, reversible or irreversible for constant P. Okay, so this is quite nice. We have just shown that delta Q, reversible or irreversible constant V is equal to dE, delta Q constant P, reversible or irreversible, is equal to dH. So if you're doing a constant pressure or a constant volume process, the heat that you give to a system does not depend on the path you take. It's just a state function. Okay, so that's super nice. We are now ready to introduce something which is quite important in thermodynamics. It had showed up when I think Suimin posted the answer to one of the problems, and she knew it, so she introduced C symbol, and everyone was like, where did the C come from, right? So now we're going to talk about C. Now we can introduce heat capacity. Heat capacity is defined as CV, can be defined in two ways, at least two ways. Heat capacity at constant volume, that is delta Q by delta T at constant volume. Will the heat capacity be a state function or a path function? So, okay, let's look at it first for a moment. What is heat capacity? It is the amount of heat you need to give to a system in order to change its temperature by a certain amount, right? It's delta Q divided by delta T. So I have a block of a certain material and I have to heat it to raise its temperature by 1 Kelvin. And let's say this is coffee. Now, if this heat capacity was path function, then it would depend on whether this coffee was, I don't know, finely ground or filter coffee or things like that. But it's not true, right? Normally what you have to heat it, the amount of heat you have to give does not depend on whether the coffee beans came from Guatemala or somewhere else, it just doesn't matter. Can you see that? Why that is true here? Why do we know that CV is a state function? Go ahead. Anyone? Yeah.
Because it's the constant volume process. So delta Q is a state function.
Exactly. This is delta E by delta T at constant volume, right? And you're differentiating E with respect to T, a state function with respect to T at constant volume. That's why it's a state function, right? So similarly, Cp, which is delta Q by delta T at constant pressure, is equal to partial H by partial T at constant pressure. And that's also going to be a state function. So these two are state functions. So I really like heat capacities, and that's for two reasons. One reason is because I have my favorite qualifying exam question that I always ask. Many of you will be in calls with me and I will ask you. So if you remember today, you will be good then, otherwise you will forget. One of these is always more than the other one. Can you see which one?
CP.
Why?
I need the formula.
You need the formula, not the formula. I'm asking for intuition. So yeah, go ahead.
D is greater than DH in a sense.
Don't be careful with the denominator. You have a partial over here, right? If you were able to ignore the partial, then sure, you're absolutely correct. So you're Nathan, right? Nathan's argument was like, well, H is going to be more than E because H is E plus PV, right? And pressure is positive, volume is positive. But what Nathan ignored is that there is a derivative at constant volume, constant pressure. The answer is physical. The answer is, I'll get to the answer in a moment, okay? First, let me tell you, I said there are two reasons why I like this so much. So the first reason is that Cp is always more than Cv for an ideal gas, for a real gas, for anything. Okay, and we will prove this. I will first give you an intuition as to why this is true. Then I will derive an expression for an ideal gas, and then you can derive some complicated expressions which are true for absolutely anything. But this is true in general for any material at all. The other reason why, and this we will prove in just a second. The other reason why I like it a lot, we won't do in 684, we will do in 687, which is one of the first triumphs of quantum mechanics. And something that even Einstein got wrong. Okay, so the question is, how does the heat capacity behave with respect to temperature? People had measured, and this could be Cp or Cv, it doesn't matter. Okay, let's just call it Cv. So this is out of syllabus. Okay, this is not relevant for this semester, but hopefully it will. Thermodynamics can be dry, and things like this, at least to me, inspire me once in a while. Like, why should we care about all this? Because if Einstein cared about it and you are saying I don't care about it, then you're one snooty person, right? I mean, clearly mattered. This defined humanity, right? I mean, our progress in the last 100 years, things like this. This was one of the first triumphs that showed people that maybe quantum mechanics is correct in the early 1900s. So does anyone know how heat capacity behaves with temperature? Have you seen the behavior? So at very, very high temperature, it becomes constant. And if you have done your physical chemistry or materials, it's got a name. It's known as Dulong-Petit law. This is known as Dulong-Petit law, and it effectively says that Cv becomes 3nr. Okay, it's heat capacity, and at very high temperature, everything becomes an ideal gas. Right, every degree of freedom is independent with each other. So just every degree of freedom contributes a certain amount to the heat, and that's it. You multiply it together. The interesting thing happens as you decrease the temperature. It starts to go down, something like this. Yeah, so there are two things here. First of all, CV tends to 0 as T tends to 0. And secondly, CV is proportional to TQ as T tends to 0. Okay, and this was a big problem that science was not able to explain. Both of these. Without using quantum mechanics, you cannot prove that CV tends to 0 as T tends to 0. And I can give you a flavor for why this is true, because quantum mechanics says that energies are quantized, right? At 0 temperature. If you had a continuum system, you could always excite it by a slight amount, right? You give it a little bit of heat, it just, if reality was like an elastic band, even at 0 temperature, you could give it some amount of heat and the elastic band would stretch a little bit. But there comes quantum mechanics, which tells us that reality is not like an elastic band. Reality is quantized, right? So some point, the temperature will become so small that it is smaller than the smallest quanta of energy, right? H cut omega. And then even if you give it some heat, the system will be like, what do I do with this, right? You can't do anything with it. So it just stays where it is. So the heat capacity goes to 0. So this cannot be explained using classical mechanics. This requires quantum mechanics. And this one, Einstein got it wrong. Einstein's heat capacity went like e to the power, forget, minus alpha by T or something like that. And it was Debye who got it right. And we do this in 687 as to how this really follows. So heat capacities are very important. And in statistical mechanics, you see how you can actually derive these expressions and where they come from. So this will happen in Chem 687. Well, depending on who teaches it. If I teach it, then I will do it. Otherwise, some people ignore it. So in David Chandler's book, this is just a homework problem, exercise problem. So, but now let's come back to CP more than CV as to where is that coming from? And I'm going to give you the physical intuition first, then I will do a bit of math and get to things. Okay, so why is heat capacity at constant pressure more than heat capacity at constant volume? So let's imagine a container of gas with constant volume. Okay, so this is some gas. Imagine the same container of gas where there is no constant volume and the gas can expand, right? And you give heat to this gas, the same amount of heat you give to both of these. You give delta Q and delta Q. So, and let's say overall this is well, no, I don't need to draw insulated. I'm giving heat, so that kind of makes it nonsensical. I'm giving heat to it. And the gas in the first case, this is constant volume and this is constant pressure. So in the first case, what is heat going to do? It's going to excite the molecules of the gas, right? They will go crazy. They will start bouncing around more. Its temperature will increase. But that's it. That can happen. There is no other process that's going to happen, right? So in the first case, delta Q is equal to dE, right? In the second case, when you give heat to the gas, it not just gets hotter and hotter, but it also expands against the atmosphere, right? So in the second case, delta Q is equal to dE minus P external dV. No, I wrote it wrong, right? I was like, wait, this would mean CV is more than CP. dE is equal to delta Q minus P external dV, right? That's first of thermodynamics. And we know dV is positive. So you can see D is going to be smaller than delta Q, right? So in constant volume process, you get more bang for your buck. Okay, whatever heat you give goes into making the system jiggle more and more. And that's the origin of temperature, right? In the second case, yes, the gas starts to jiggle faster, gas molecules, but they also expand. And some of it is lost into doing pressure volume work. Okay, is that clear? So if you take your qualifying exams with me, or even your chemistry cumulatives or something, I will probably ask you this question. And yeah, but that's another story. So we will look at expression for this, but intuitively, we have just shown CP minus CV is positive, right? It takes more heat to change the system's temperature by a certain amount if you're doing it at constant pressure, okay, as opposed to constant volume. And we will derive expressions for this. Before doing that, I want to take one moment to think about CV and point out a mistake that people make in thermodynamics all the time and it's important to understand it carefully. So we defined CV as delta Q by delta T at constant volume. Okay, this is true for any material. We then said this is partial E by partial T at constant volume, and this kind of connects to Nathan's attempt to prove that Cp is more than Cv, which is exactly how we will derive the expression for ideal gas. Okay, this is also true for any material. Now let me write down an expression for you and ask you whether it's true or not. Oh, where did I get a U from? dE by dt. And I have gotten rid of the partial. Is this true? Will it ever be true? So for example, Nathan, what you said, your argument would have worked, right? If this was true. If there was no partial, you would have said Cv is dE by dt and Cp is dH by dt, right? And H is more than E. So there we go. And we can in 1 second, we can derive an expression for Cp minus Cv. This is true for an ideal gas. Okay. So when I teach undergraduate thermodynamics, which JP took, a lot of students, like half the class makes this mistake. You get stuck in a derivation. You make a last ditch attempt, just get rid of the partial and change partial E by partial T at constant V is equal to dE by dt. And magically, half the algebra disappears and you get the answer. So don't do that, okay? You're all very respectable PhD students. So how do we show that this is true for an ideal gas? How do we do that, right? Why did this happen? So in order to do that, let's consider energy as a function of T, V, and N. At this point, one of you will probably go, well, those are not natural variables. You are absolutely correct. The natural variables for energy are different. But nothing stops me from writing energy as a function of these, right? It's a function. It's maybe a partial differential equation, but it is a function. I can write it. Whether this function is useful or not, that's the story. But I can always write it. So in fact, Callan talks about this at some point, and he says that this function is low information content because we know it is not thermodynamically complete, right? For thermodynamical completion, you need it to be, anyone remembers what are the natural variables for E? S, V, N, right? You can't have temperature. Remember, because we showed this, right? Temperature is a partial. This is a PDE, this is a partial differential equation. So Callan says this is low information content, but high truth content. Okay, it's true. There is nothing wrong in it. It's just like it's not informative. It's missing some information. When you do things with it, you will have undetermined constants and things like that. But we can do that. There is nothing wrong stopping us from writing it. And let's focus on constant N system. So we don't, just for simplicity, so we don't have to worry about if we did a variable N, then we would have a chemical potential. So let's focus on a constant N system. In that case, E is equal to E of PV. And this is not ideal gas or anything. This is true for any, you have some equation. You don't know what this equation is. Once we have something like this, we can write down dE. dE is going to be partial E by partial V at constant T multiplied by dV plus partial E by partial T at constant V multiplied by dt. Which of these partials have we just seen? Have you seen this one? That is CV, right? So this is plus CV dt. But this terrible thing lingers. And if somehow this thing was be equal to 0, then we would get this to be true, right? So this partial E by partial V by T, what does it look like? What's going to be its dimensions? What is the dimension of energy over volume? Huh? Pressure. Why?
Because
Well, we have seen it in first law, right? dE is equal to PdV. Remember dE by V. So this is sort of a pressure. So we give it a name. We call it internal pressure. Okay. Let me just check one thing. Huh? It's a pi. It's a pi. How many digits do you remember pi?
1.
Come on, man. Don't disappoint me. Here's the challenge. If anyone here remembers 5 more digits than me, I will buy you a coffee. Who wants to take me on right now? Huh? At least 35. It's 3.1415926535897932384626433827950328. When I was in grad school at Caltech, I have actually won beers by this. It's a very nerdy place, So you go to a bar and you say, "Hey, will you buy me a beer if I tell you 5 to 20 digits?" People say, "Sure."
Well, couldn't you say anything?
Huh?
They don't just believe you, they don't know.
No. Everyone takes the phone out. Take your phone out and check. I'm not BSing. Let's bring it on.
How many digits is it?
I will write it down for you. He's challenging me. Look at his audacity. 3.14159265358979323846264. Wait, 33832795028. That's 35. And you know what? Since I like you so much, I will add you 4 more digits. Then I think it's, but I'm not sure about these. You can't believe me.
You're right so far.
Of course I'm right.
Yep, those digits are right as well.
Are these also correct?
Yeah, the last.
Oh, good. So I'm up to 50 now. So no, there's a trick. You can remember this when I first started. Yes, I need a drink, alcoholic, of course, after the heavy sessions involving quantum mechanics. That was a pure distraction, and this is not going to be in my, maybe I'll leave it. So whoever is not attending class will be like, "Excuse me, is that on the exam?" And then we will not tell them. So, okay, before we go further with pi t, it looks like partial E by partial V, so it's pressure. We did define pressure more rigorously. That was also partial E by partial V. What was different there? We have defined thermodynamic pressure, right? You did it in your first homework. You showed it is related to empirical pressure. Remember, it was partial E by partial V. It was natural variables. So what are the natural variables for E? V, S, and N. If you're doing partial E by partial V, what must be held constant? S and N, right? So true pressure is partial E by partial V at constant S and N. That's why we call pi t as internal pressure, okay? So this is true for any material. dE is equal to pi t dV plus CV dt. If we could calculate pi t, then that's suddenly very, very powerful, right? Because we have a way of calculating dE for that material. Turns out heat capacity is quite easy to measure. On complicated systems, people have been measuring heat capacities. In fact, I just told you that these plots for heat capacity existed for a very, very long time, way before 1900. And actually, I want to write down one thing here before I forget. So this is AT cube, but the truest description is AT cube plus BT. Does anyone here know where does the BT come from? That's due to electrons. So the phonons contribute heat capacity as AT cube. The electrons contribute heat capacity as BT. And in real materials, there is electron phonon coupling, and that leads to more complication. And we won't do that even in 687. But let me come back here. So heat capacity is, the message being heat capacity is important. People have been measuring it for a very, very long time. So what did I write there? I wrote down dE is equal to pi t dV plus CV dt. Okay, so now let's think about pi t. Pi t is partial E by partial V at constant T. What will pi t be for an ideal gas?
It's the same as the actual pressure. It's constant.
There's not that many answers. You guys are saturating all of them. What is energy for an ideal gas? 3/2 nRT. Does it depend on volume? So this is 0 for ideal gas. What is pi t for a van der Waals gas? It's very interesting. It's actually minus an square by v square. Yeah, and I challenge you to prove it without using Maxwell's relation. This happened 2 years ago when I was teaching undergraduate PChem. I looked at this expression, it looked like makes sense, right? Because that is the term that comes in the van der Waals equation, but I had not taught entropy then. And I asked him to prove it. And turns out you just cannot prove it. And this is another one of those examples. You need to have, if you're thinking of energy as a function of NVT and not as a function of NVS, you cannot derive this expression. This is a classic example of thermodynamic incompleteness. We will derive this expression later for van der Waals gas. Right now, we cannot do this. It will take us, you can do it. Effectively, you will end up deriving Maxwell's relation, but without directly using it, it's hard to do. We will get to that later. So later we will see that pi t is equal to minus an square by v square for an ideal gas. But for now we know, for a van der Waals gas, for now we know that pi t is equal to 0 for an ideal gas. Therefore, dE is equal to Cv dt for ideal gas, or Cv is equal to dE by dt for ideal gas, right? So for an ideal gas, there is no partial derivative, there is no nothing, because it makes sense, right? Ideal gas, the equation of state, it's kind of obvious, right? Because the equation of state itself, it just depends on nRT, right? There is only temperature in this one. Yeah, it's simple. In the equation of state for energy. So what will dE? Yeah, we will do the van der Waals thing later. We have to do Maxwell relations for that first. So now let's derive an expression for Cp minus Cv, which is true for ideal gas. We are basically ready to do that. We have looked at all the math, and then we will stop for today. So let's calculate Cp minus Cv for ideal gas. Okay. We know it should be positive, but let's actually calculate an expression. So Cp minus Cv, what is Cp? Cp is partial H by partial T at constant pressure. What is Cv? That is partial E by partial T at constant volume. We are doing ideal gas. What should we do next? Any ideas?
Well, we don't need the constant volume, right? So we just have the whole.
Okay. So we can just write down the expression for energy, right? We just said that for the ideal gas. What was that? That was 3/2 n kBT. And instead of R, I'm writing Boltzmann constant because n is measuring number of atoms instead of number of moles, you know. We are all semi-physicists, so it's just a scale. So partial T at constant volume, right? That we can calculate. So this is going to be partial H by partial T at constant T. Minus 3n kb by 2. That's it, right? Now we still have something left, and we have to think about H. What is H? H is equal to E plus PV, right? Therefore, Cp minus Cv is equal to partial E by partial T at constant P plus partial PV by partial T at constant P minus 3n kb by 2. Is it okay? Or did I make a mistake? I don't think I did. What can we say about this one? It's the same thing as the other one, right? So this is actually going to be also 3n kb by 2 plus partial PV by partial T at constant P minus 3n kb by 2 this and this cancel. So if we had not calculated explicitly, just realize that energy does not depend on, pressure or volume, it would have been already there. So we have this. What can we say about PV for an ideal gas? That is nRT, right? So this is partial nRT by partial T at constant pressure. Well, there is no pressure in the function we are differentiating. So this is simply nR. We just showed that Cp minus Cv is equal to nR for ideal gas. And the amazing thing is there exist exact expressions for the heat capacity difference for any material, which is very useful because you want to calculate the heat capacity. And maybe for your material, it's easy to design an instrument which is constant pressure or constant volume, right? If your material is, I don't know, if it's a frog or something. And if you design a constant pressure instrument, the frog will jump out of the instrument, right? And it's not good. So maybe you want to do constant volume experiment on the frog, but you want to calculate the heat capacity at constant pressure for the frog. And these equations will allow you to do that. If you assume the frog to be an ideal gas, then you know how to do it already. But the frog is probably not an ideal gas. So, and you will remember that Cp is always more than Cv. So, next class, what we are going to do is to use this du is equal to pi t dv plus Cv dt for an ideal gas, where this one just goes to 0, to derive a bunch of useful quantities. For example, the practice problem that I gave in the Slack, we will do things like that and come up with, so I'll write down what we are going to next time, and you can find it somewhere in Callan or even just online. So next class, we will study adiabatic reversible expansion of an ideal gas, and we will show what is the equation that governs such a process. Then what we are going to do after that, so you can read up, and then it gets a bit abstract. It's useful if you read it. Then we will move to something known as a Carnot cycle. Why will we go to a Carnot cycle? Because we have kept saying that the maximum work that you can get out of a system can be done if the process is reversible, right? So if the process is irreversible, the work that you can get out of the system is going to be smaller than that. So you can think about this defining an efficiency, which is the ratio of these two, right? So if it's a fully reversible process, the efficiency is 1. And then we will show a cycle which can actually reach the maximum efficiency that is possible. And that has been, a lot of people, when they do thermodynamics, they find Carnot cycle to be abstract, but it is really how thermodynamics started. And it's for a variety of reasons, it's important to consider it. If you skipped it, you will still be okay in what we are doing next, but every once in a while, you will feel that there is like a vacuum in your life. Okay, so we will do Carnot cycle, and then we will get to free energies. That's the game plan. Let me write down more. So if you want to read them, free energies, we will first introduce free energies from a practical need, okay, as to why do we need these free energies, and then we will introduce them from a more mathematical need, and that's where we will face your good friend Legendre transforms, okay? And once we do this, then we will move to more, and we will start getting more and more applied. For example, we will answer, yeah, we will keep getting more and more applied. For example, one of the things we will answer in this class is, how does ice skating work? Maybe, or lots of other practical things. We will do phase diagrams, etc., etc. So this is going to be next few classes.